Starting out this lecture, we just finished off in the previous one, setting up this equation here from the original chemical equation. This is the equilibrium expression. And to give a general idea how this kind of goes, as long as we know the reaction is elementary, that there's just one step, it's not multi-steps. Again, this is a very general idea of how an equation could look. We have the equilibrium constant, K, is equal to the products over the reactants. So the concentration of C raised to C, concentration of D raised to D, concentration of A raised to A, and the concentration of B raised to B. And again, the general idea is always products over reactants. Okay, works great. And again, what we're looking at here, generally speaking, we're looking at concentrations. That's what these brackets stand for. So think aqueous solutions. We could also look at it in regards to gases, but we'd be looking at it still in regards as concentrations, the moles per liter, moles per liter. Okay, if we want to look at it as far as pressures, we can actually do that too. In ATMs typically is how we look at it. We can look at an equilibrium expression for pressures. And the equation for that, and you have this in your packet. I'm going to put a little C here. There's lots of different ways you can put these little sub symbols on the equilibrium expression. We could just leave it as K. We could say KEQ. We could say KC. They all kind of mean the same thing. KP is equilibrium expression, but we're looking at pressures. Also, one thing to mention is that these K values are unitless. It's a ratio of the products over the reactants. So there are no units attached to it. Kp is equal to Kc, kind of like we did here. But, and there's a way we can derive this equation. We're not going to bother with that. We're just going to fire away and say, yep, that's it. So we have the equilibrium expression of concentration, multiplying it times the R value. And the R value is going to be based on atmospheric pressure. So ATMs. Therefore, you're not using it 8.314. Make sure you're certain of that. We're going to be using the 0.0821, and we'll write it down in a minute. Temperatures in kelvins, and this is the difference in the number of moles of products and reactants of gases. And I'll write all this down. Okay, let's begin. Kp is equal to the equilibrium in regards to partial pressures of the system. It is not molarities. Kc is equal to equilibrium in molarity, concentration. R is equal to 0.0821. And just so we're familiar with all the units, ATMs times liters over moles times kelvins. Temperature is in kelvins. Just so we can see it, kelvins. Now delta N, that's kind of a new one, is again, it's going to be products. I don't know why I made that so large. Products minus reactants of moles of gases. And this is all from the balanced chemical equation. And again, we're only looking at the moles of gases. Let's see, I can probably squeeze this in over here. Now, just based on your little math skills here, Kc is equal to Kp when, anyone? When the moles of gases are equal. So just make sure you're using the correct equation depending on what you want to actually look for. If they're giving it to you in ATMs, you can use that, or you can use the Kc. Either one is fine. It's just when you're transferring back and forth from one to the other. They have different values, but they're independent of each other. Okay, we're going to go over and do a homework problem. Number 12. So you've got this little drawing here in your notes. The following graph represents the yield of the compound AB at equilibrium in the reaction, right here, at two different pressures. And this is a little bit off here. That's fine. X and Y as a function of temperature. Okay, fine. First question, which is on the other page, your next page, is the reaction exo or endothermic? And remember, temperature is really a function of energy. So endo or exothermic has to do with that. I'm going to help you out with that. So I can see as the temperature is increasing, going in this direction, I can see that the concentration of both of these guys are going down. As temperature goes across here, the concentrations are going down. Fair enough. Now, this is something that is going to become a lot more clear, crystal clear, as we get further into the lectures. At this point, unfortunately, I'm just going to have to just tell you, and you're going to have to say, if you say so, whatever. The fact that as temperature goes up, that this goes down, that actually tells me that energy is a product. And I go, at this point, this doesn't make sense. Why? Let's just go with the fact that energy is a product. It's exothermic. Now, when you add either one of these guys here, it was balanced out, but when you add any of these in here, it has to rebalance and shift in the opposite direction. So because I'm adding energy, I have to shift in the other direction. Again, just work with me on this. So I'm going to answer that question over here. Your sheets will probably be fine, but this is the way mine are kind of set up. So we're just going to go with this. We will say it is exothermic. And the reason it is energy is a product. And products decrease when energy is added. Okay, fair enough. Next question. Is pressure of X greater or smaller than the pressure of Y? Well, if we take a look at this, we can pick any 2 points on here at the same temperature, looking at it. And at all temperatures, every single time, pressure of Y appears to be higher than the pressure of X based on the concentration. And also, I get to talk about concentration. It works the same way. So the question is the pressure of X greater or smaller? So yes, for every single time, the pressure of Y is greater than the pressure of X. And again, that's just making the relationship based on where the pressure is and the concentrations are. So that all works out. All right, that one is done. Let's go ahead and do 21 as well. Looking at 21, find that on my sheet here. 21. If Kc is this value for this equation here at 500 Kelvin, what is the value of Kp for this reaction, this temperature? So we sort of just kind of set this one up. Let's see if we can put this together. Again, the equation we have is Kp is equal to Kc RT delta N. And we know what Kc is. We know what the temperature is. We have the equation right here. This should just fill itself in. Kp is equal to, Kc is 0.042, R value 0.0821. I won't always put the units in here, but I will for this one. Moles per Kelvin times temperature, 500 Kelvin. And as far as the moles go, let's take a look. It's going to be, again, products minus reactants. For the products, I have 1 mole, it's a gas, minus 1 plus 1 is 2. So 1 minus 2 is negative 1. And if I plug all that into my calculator, I'll get 1.02 times 10 to the negative 3. There we go. That one is done. Right, that's the end of the second lecture.